Number 47. Find the electric field at the location of QA. In figure 18.53, given that QB, QC, QD all equal 2 nanocoulombs and Q is equal to negative 1 nanocoulombs and the square is 20 centimeters on a side. All right. So problem sounds hard, but it's actually fairly straightforward how to do it. So remember, electric field is a vector. So if you want to find the electric field, the net electric field at Q sub A, right, at this particular location right here, then all we have to do is find all the vectors at that point, or find all the electric fields at that point, and then just simply find the resultant. That's all. It's that simple. All right, so this is something, this is a concept very similar to forces that we've studied in the past. We get a whole bunch of forces, right, acting on an object, and you're going to find the resultant force. So same idea. So what we can do is let's take a look at each of these pieces individually. We got 4 charges here, each producing an electric field at this particular location. By the way, it doesn't have to be at a certain charge. You know, it could have been here, for example. Find the electric field at this point, right? I mean, you'd have to know some distances and stuff in order to find that exactly, but it doesn't really matter. It doesn't have to be at a charge, all right? So that being the case, you know, pretend this isn't a charge. Let's just pretend it's a point here. And by the way, right, why can I kind of ignore the charge for Q sub A? Well, what's the electric field, right, produced by Q sub A at Q sub A? Well, it's kind of undefined, right? Why? Well, look at the formula for electric field that relates the charge to the and the length, right, to the particular point of interest and the electric field. It's K times Q all over R squared. So what's the distance, you know, between this point of interest and QA? Well, it's at the same point, so the distance is basically 0, right? So this thing basically becomes undefined, all right? So just like I was mentioning, just disregard the charge. It's not even going to be part of the problem. So now, let's take a look at let's take a look at Q sub B's effect on on the electric field at this particular location. All right, it's going to be pointing to the, what do you think, left or right? Well, we got to know the charge, right? So this is positively charged, and therefore the electric field lines always emanate away, right, from that particular point. And therefore, at the point of interest over here, we're going to have a vector pointing to the left, right? That would be the electric field produced by B at this particular point. So how about C? Well, again, they told us that it's going to be 2 nanocoulombs positive. So let's put that in as a positive. And we know that that's now going to be pointing upward, right, at that particular location. So that's the electric field produced by C. How about D? Again, D is going to be positive, right? So that is going to be, and again, right, all the lines move away from D, right? So then at this particular point of interest, right up here, we're going to have a vector pointing that direction, okay? Let me make that just a tad neater if I can. Yeah, that's good. And that's going to be now E sub D. And last but not least, we got this little q here. I'm going to put that in red. The reason why is because it's a negative. Remember, lines always point toward the negative charge. And therefore, from this particular location, we're going to have a vector pointing in that direction. And guess what now we need to do? So this is the electric field caused by just the q. All we now need to do is what? Find the resultant electric field there, okay? So we can break this up and we can study this in terms of our component table. Whoa, blast from the past. We haven't seen that component table in a while, right? So here it's going to be the x components. And here we will then draw the, right in the y components. All right, and then here we're going to put the vector, okay? It's just a table that helps to organize your thoughts. So let's call this vector E sub B. Let's start with that one. Doesn't really matter which one you start with, E sub B. So what is the x component value of E sub B? Well, that's some number, right? So why don't we first do this? What is the electric field being produced? What is this vector, right? All that vector is, if I'm going to do the calculation on the right-hand side, is just the electric field produced by charge B at this particular point will be equal to the electrostatic constant K times the charge of B, all divided by then the distance between charge B and the point of interest squared. Okay? So I can easily calculate that, right? So what I'm going to do is I'm just going to plug in, though, the formula in here. Instead of the number, should I plug in the number? Well, yeah, why don't we plug in the number quickly, okay? So E sub B, I'll probably do one of these calculations and then it might be better to simplify. Yeah, I'll do the calculation. All right, you can also simplify this with all the formulas. It doesn't really matter. This is going to be 8.99 times 10 to the 9th multiplied by that charge is going to be 2 nanocoulombs, so it's 2 times 10 to the 9th. All then divided by the distance between them. They said that it's a square, 20 centimeters on a side, which means that this distance between the point of interest and that charge is going to be 20 centimeters, aka 0.2 meters. Okay? So let's plug that in. So that's going to be 0.2 squared. And let's get now E sub B. Okay, let's see what we get. So we get 8.99 times 10 to the 9th multiplied by 2 times 10 to the minus 9th, all divided by 0.2 squared. And we have about 449.5. That's newtons per coulomb. Okay, those are the units. So now let's plug that in for our x component for the vector E sub B, right? E sub B has all x component. Now remember, when you plug this in, make sure you plug in the signs in your component table. Since it's pointing to the left, it's a negative. So this is negative 449.5. Now what's the y component of this particular vector? Well, it's 0, right? Because it doesn't point, it points in the pure x direction. All right, moving on, E sub C. So E sub C is here, right? And now if you notice, right, Q sub C had the same charge as Q sub B, and the distance between the point of interest and the charge here is going to be the exact same, right? That's going to be 0.2 meters. So essentially, E sub C's magnitude is exactly the same as E sub B's magnitude. However, it's pointing in a different direction. So that's all we have to take into account, right? So what's the x component of E sub C? Well, it's 0. It's pointing in the pure y direction. How did we know that too? Well, remember, it's a square. All right, this whole picture is a square, so that should hopefully make sense. So the x component is 0, and the y component is pointing upward, so it's a positive 449.5. Great, moving on. How about now E sub D? Okay, and let me just move these lines, make them a little longer. Voila. Now how about E sub D? Well, take a look at the picture. Right, E sub D now is this vector. It has the same, it has the same charge value, right? I mean, the electric field being produced at that point has the same charge value because all these charges are the same, but the distance is now what has changed, right? So basically now what I have to know, and I'm probably going to erase this line just so it doesn't look too confusing, I got to know that particular length. So how do we find this particular length, right? What do you think? Well, you know it's a square. So that means if you know it's 0.2 meters on that side, you also know that it's 0.2 meters on this side, and OMG, we created a right triangle. So that means we can find this hypotenuse, right? So just remember it's a squared plus b squared equals c squared. Okay, in other words, you can simply find that hypotenuse here. You can simply find that hypotenuse by simply taking the square root of the a side squared, so 0.2 squared, and adding it to the other side squared. So let's just find that. So second square root of 0.2 squared plus 0.2 squared. Could have also multiplied it by 2. It doesn't really matter. So the length here of that hypotenuse, so I'm going to label this r now, is going to be 0.2828 blah blah blah. Okay? Now when I calculate the electric field, I now need to say the electric field at point D will equal K, which is 8.99 times 10 to the 9th, times the charge of D, which is again 2 times 10 to the minus 9th. It's the same charge as the other ones. All divided then by the radius here, so it's going to be 0.2828. And actually, technically, you probably didn't even have to do this. Because if you plug this in, right, and then you squared it, it gets rid of the square root. So essentially what you could have done is you could write that number in there, that's fine. Or you could write in, just to give yourself a real exact answer, 0.2 squared plus 0.2 squared. Okay? And the electric field here at E sub D will be 8.99 times 10 to the 9th times 2 times 10 to the minus 9th. Then all divided by parentheses, 0.2 squared plus 0.2 squared. and I get about 224.75. So 224.75. Okay, cool. So now let's plug that into our table. Now, well, so where do we plug that in, right? That's the key critical question. So this vector here represents the magnitude, or that magnitude, I should say, represents this vector up at the top, E sub d. Now, what's the x and y component to that? Well, you're going to say, well, it has both x and y, so what do we got to do? Well, what we have to do then is we have to find the components of that vector. How do we know how to do that? Well, we got to know some angles. Now, remember, this whole thing is a square. So that means you know all these angles. This angle in here is 45. This angle in here is 45, right? This angle in here is 45. That angle in there is 45. You're all going to have 45-degree angles here. So if this is the total vector, right, and you have to find the x component, all we have to do is multiply this value by the sine or the cosine of 45. And the sine or cosine of 45 is the exact same value. So it really doesn't matter which one you choose, all right? So multiply that by now sine of 45. So it's 158.9. Okay, so this really, so the electric field produced by charge D in the x direction will equal, and I'm just going to plug that now right into the table. Okay, it will equal negative, because the x component of that vector is pointing to the left. It's going to be negative 158.9. So 158.9. And then the y component is going to be the exact same magnitude, but it's pointing upward, right? So it's going to be positive 158.9. Okay, and that takes care of E sub d. So now, hopefully that's good. And now last but not least, finally, right, we can calculate now our, and I realize I should have, let me put that in black. 1 second, guys. Because the other one I chose to do red. So 158.9, 158.9, negative 158.9. All right, cool. And now last but not least, we have the other vector. This is now going to be E sub q. And we know here, let's erase this. So now remember, if you know this particular distance, you can find half of that distance now, because I'm talking about q. So I got to find the distance between this point and the point of interest, right? That's half now. So you can basically just take half of these values. This will be 0.1 squared and 0.1 squared when we calculate. All right. And if not, if that sounds a little confusing and that was fast, try to draw it out. Right? Draw the picture out. Maybe I shouldn't have erased all that. Yep. So okay. So let's erase this in the picture, since we don't really need that anymore. Oops. Oh, man. Well, this means opportunity for small talk. How you guys doing today? Hopefully doing well out there. All right. Semester probably, well, actually, you're probably in the thick of the semester if you're watching this video, or reviewing for your final. So it's either going to be a good time or a bad time. Well, actually, both might be bad times, but at least one, you see the light at the end of the tunnel. So, all right. Anyway, enough of the small talk. Let's get back to physics. So we know half the distance, right? It's going to be half the distance of what we found before. And the charge here has changed. So now to find the electric field of Q at this particular point is going to be the same formula, K times Q all over R squared. K is going to be 8.99 times 10 to the 9th. Q here is going to be the charge value, and they told us it's negative 1 nanocoulombs. Now you don't plug in the negative sign. All right, the reason why, just plug in the magnitude. You know you're going to determine the signs based on your picture. And before, this is what I was kind of talking about. All right, that it's best to not include the signs and use pictures, all right, to help yourself out here. Because the negative, it has a positive x component, but then it has a negative y component. How would you figure that out if you just plugged in a negative sign here and you got a negative value? Right? It'd be basically impossible. So, and the other problems it was working, but this is basically what I was mentioning, that it's best to just plug in the magnitudes and then think about the signs based on your pictures. So here it's going to be 1 times 10 to the minus 9, divided then by the distance. So now remember, in terms of your picture here, this would be point, right, if I had to draw a quick triangle, this would be 0.1, this would be also 0.1, and then you'd find that total length there, the hypotenuse. All right, so you can basically do the same ideas we did before here, with the denominator, except that instead of 0.2, it's going to be 0.1. So this is 0.1 squared plus 0.1 squared. Okay? And the square of the denominator got rid of the square root when we solved, so all the same reasons as before. So let's do it. 8.99 times 10 to the 9th multiplied by 1 times 10 to the minus 9th, all then divided by parenthesis 0.1 squared plus 0.1 squared. And we're going to get about 449.5. Okay, great. And now from here, we know the magnitude of that vector, but we need to find the components, and therefore, remember, we have to find the x, right? We have to find the x component and the y component. So we know this angle in here is 45 degrees, and therefore we can just multiply this by the sine of 45 or cosine of 45. It doesn't matter. Sine of 45, and what do we get? So now for the x component, it's going to be positive as indicated by my picture. So it's going to be 317.8, so 317.8. And then the y component here is going to be negative 317.8. So voila, we got all the values in the component table. And all we now need to do to find the resultant vector is to simply add up all the components and find that resultant. And that's it. Just add up the x, add up the y, then you have the components of the resultant vector in x and y. All right? And then we can do our resultant formula on that. Very, fairly nice here, right? So let's do the x. So negative 449.5. And that's going to be now minus, let me see if I can get the exact value, 158 point whatever. Just got to go back in the calculator a little bit. Yeah, 158.922, whatever. I'm going to use the exact value there, and then add to that the exact value, the 317.8444. And what do we get? So here we get a value now of about negative 290.5. We'll go to 58. Okay, great. Same thing now with the other side. Okay, so it's 449.5. Plus then this 158, right, 0.9. I'm going to get the exact value again. There it is. And then minus now the 317. And I get a value of 290 now, 0.5. 290. 290.5. 8, right? And let's calculate. So now, so I'm going to erase some of this beautiful work. Okay. So now we found the components of that resultant vector, okay? And almost there. All right. So now, if you had to just plot this, right? Pretend you had to now plot that resultant vector, on, you could plot this on the table over here. That's fine. Let me think. I'm actually going to, what I'm going to do is I'm going to, What I think I'm going to do here is I'm going to just plot, instead, because there's so many vectors on here, I'm just going to plot my own little coordinate over here on this right-hand side, okay? So how would I plot, this particular vector? Well, in the x component is going to be negative, right, 290, and then the y component is positive 290. So I got to go 290 units to the left, 290 units up. So basically it's like a point here or so, and I would draw in my resultant vector. And it didn't really match the dot, but that's fine. Okay, cool. So now here's the magnitude. Here is the vector, and we know like I was mentioning, we know the x component and the y component. So now how do I find the magnitude if I know the x and the y? Well, you can use Pythagorean's theorem, right? Use Pythagorean's theorem, or you can simply use this resultant formula. And this is a blast from the past as well. This is going to be square root of the sum of all the x values squared plus the sum of all the y values squared. All right? So this is simply going to be equal to, and that's the nice part about the component table. You literally just plug it in now. 290.58 squared plus 290.58 squared. And take the square root of it. All right? And so what do we get? We get an R value here of approximately 400, considering rounding, 411 newtons per coulomb. All right? That will be the resultant electric field. So now remember, electric fields both have magnitude and direction. So I'd also have to give the direction here. Now, these angles are all 45. And the reason why you know that is because these components, x and y, are equal. All right, in magnitude, that will always be the case. So this angle's 45, this angle's 45, this is 90. You can add the 45 and the 90 together if you'd like to find the, angle from the positive x-axis. It doesn't really matter. I like to choose the acute angles. But they all should mean the same thing in the end. All right, so the electric field, the resultant electric field here, should be equal to 411 newtons per coulomb at, I'm going to write it as 45 degrees north of west. All right, and you could have, written that as 135 degrees, from the positive x-axis. Doesn't matter. They're the same thing. So guys, thanks for tuning in. Please remember to subscribe and help us out. If this video helped you out at all, that'd be a really great way to help us out, help our channel grow, help us keep doing what we're doing. All right, so yeah, we appreciate it. All right, hopefully this helps you. Thank you.